How's it going, everybody? Here we go. Back at it. We got some more dynamics. Let's jump into what we can do. All right. So this one says the 28 megagram bulldozer is originally at rest. Determine its speed when t equals 4 seconds. If the horizontal traction varies with time as shown in the graph. All right. So first thing they do, they give us some mass. 28 megagrams. All right. Mind you, 28 megagrams is the same as 28,000 kilograms, right? Because a megagram is 1,000 kilograms. This part right here is a megagram. So 28, just put on 10 to the third kilograms. Cool. Let me write that in blue, actually. So they give us that, mind you, when they give us mass, we got to start thinking. You already have to start processing information and saying, what am I going to work with? So once you see mass, you know you're going to either do a free body diagram, work energy, or impulse momentum. Those are going to be, one of those three is going to get you the answer, right? Maybe you might need to use two of the three, but one of those three, when you solve it, is the answer. So which one I don't quite know yet, but the moment I see mass, I know I have at least that. Say it's originally at rest. All right, cool. That means that the starting velocity, or V naught or V1, if whatever one you want to use, is going to be 0. All right, cool. So they want us to determine its speed when t equals 4. So they tell us time is 4, and they want the speed. So they're looking for V2, right? So basically saying V2 equals whatever. And then they tell us time, or the change in time, rather. It doesn't really matter how you put it, whether you put time or change in time. Most people are going to put t. I'm going to put delta t. It doesn't matter which one you put. That's not actually important. So I know it's 4 seconds. Let's see. What else we got? Horizontal traction varies with time as shown on the graph. So they give us this graph. This graph is huge. So we know the force as a function of time. Please pay close attention to that. They also give it to us in kilonewtons. So just make sure that whatever you do, you just multiply this by 10 to the third. Okay? Because you want to turn it into regular newtons. So you scratch out the K, put it in newtons, you just put on this times 10 to the third. Bam. That's already been accounted for. Put everything into their standard metrics. So how do we know which one we're going to use? Well, free body diagrams, it uses one place or one time, right? The primary variables, mass, force, and acceleration. Well, they're not asking us for acceleration. They're asking us for velocity, right? They don't give us acceleration anywhere down here. And so, because nothing has to do with acceleration, okay, I'm tempted to not use free body diagram. Also, if you take a look, if you look at this graph right here, this graph is in seconds, right? The graph is in seconds. And so I have a starting time, and then I have a variable, and then I can have any stopping time anywhere I want, right? In our particular case, our V2 is going to be at 4 seconds. So we're going to go from 0 to 4. So, or time 1 and time 2, V1 T1 and V2 T2, right? So we have that. So we have 2 times, which means free body diagram is not going to be what we need. All right, that's fine. Go to work energy. Work energy uses 2 places. So instead of putting 2 places, I'll just put delta S, right? S2 and S1. And the variables in play are going to be mass, force, distance, or delta S, right? And velocity. Well, I guess you could put delta V, but velocity. So I'm looking for velocity. It might help me. Velocity is also given. That might help. They gave me the force. The force is this graph. And then they gave me a mass. So I'm pretty clear on everything except this guy. That's not given. That was not given anywhere in the scope of the problem. So because of that, I'm actually tempted to not use it. The only way I could work this is if I figured out what S was, because I'm looking for my V, right? I'd have to figure out what S is to solve that equation and get my answer. So which means that work energy isn't gonna, you'd have to do something with work energy to make it work. It's not to say that you can't do anything with it. It's just say that let's just try impulse momentum. All right. So go to impulse momentum. Boop, 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 boop. All right. Go to impulse momentum. Impulse momentum, its variables, or rather, it takes into account two times. So you're going to look at T2 and T1 or delta T. Variables in play: mass, force, time, velocity. I want velocity. That's what I'm looking for, right? They gave me a time. They gave me a force. They gave me a mass. The force comes in the form of this graph. The mass and the time were just automatically given to us. I have three knowns and one unknown. That means I'm going to use the impulse momentum equation to solve my problem. So that be that. So I want you guys to always remember, always do that. It's really, really helpful. A lot of students have issues trying to figure out which path of dynamics they got to take. That's the path. That's my process. Every time I do a problem, I always think about that. Okay. After a while, you'll be able to look at it and just know. All right. And some of you already can do that. So you can always skip ahead for like the first 5 minutes because I always do this analysis. But once you get to the point where you can look at it and just be like your impulse momentum without even having to write down anything, you're in a good spot. Impulse momentum equation. We have one particle. So I need to do it for one particle. We also only have one direction, right? This thing is only moving forward. If it had two directions, or if it had mass and velocity, if it had force and velocity in, a direction that had like an angle to it, I'd have to break it into a Y version and an X version. But we don't have that. So we only have to worry about one direction, one particle. One direction, one particle impulse momentum looks like this. mv1 plus any impulse equals mv2. All right. It's all on the Y. It's all in the X direction, which is great. And so it's pretty simple. All right, let's break it apart. MV1 is going to be 0. Why? Because V naught is 0, right? So mass times 0 is 0. So what I'm left with is impulse equals mass velocity 2. I know mass. I'm looking for V2. That's what I want. I have to figure out my impulse. All right, so there are two definitions of impulse. Let me just put that here and put a red highlighter because you need to know this. This is a fundamental equation. Anything with a red highlighted underline is, you got to know that. There's no getting around it. You got to know that. So define impulse. Let's define impulse. Impulse, there are two renditions of it that most students have to know. I like to say there's the calculus form and the non-calculus form. Calculus form, the true definition of impulse is F dt, right? Put arrows on because it's a vector. You're going to use this when force comes as a function. Okay. So when f is a function of time, you use the calculus version. You actually have to take the integral. You can also, if force is not a function of time, just do f times delta t, right? And this is for when force is constant. So when f equals constant. Look at what we've got. Take a look at what we've got. We have a graph which represents force as a function of time, t squared. See that? So that's not r squared, that's t squared. I know it's kind of blurry. I don't quite know why it's like that, but that's a t, not an r. And so we have it as a function of time, which means we're going to use the calculus rendition. Okay. So come on. There we go. So I'm gonna just put this in a box as well because you kind of have to know that. Being able to differentiate between the two, otherwise you'd be stuck doing the calculus form every time, and that'd be a pain in the butt. All we have to do now is plug in for I. So I can now write the integral of f dt equals mass v2. All right. I'm looking for v2. Let me just divide the mass over. So I'll put divided by m. Move the m. All right. And all I have to do now is plug and chug do my calculus. So it's going to be the integral. It's going to go from 0 seconds to 4 seconds because they told us t equals 4 seconds. So I'm going to integrate through 4 seconds. And then I need to plug in my function. My function is 4 minus 0.01 t squared dt divided by my mass, which is 28,000 kilograms, and that's going to be what my velocity is. So all I have to do is take my integral and then plug and chug. Integral of this will be 4t minus 0.01 divided by 3t cubed. And then all of that to be divided by 28 times 1,000. All right. Now I'm going to take that bound t equals 0 to t equals 4. And so all I have to do is plug in 4, because when you plug in 0 for t, this whole thing dies away. So I'll plug in my 4 into those two, and then I get my answer, which would be 0.564. Oh, v equals and 0.564. And that'll be in meters per second. And that is our answer. Okay, so pretty straightforward. A good use of the calculus rendition of the impulse momentum equation. So that ends up working out pretty well. Pretty straightforward. It's about all we had to do was identify the impulse momentum equation, all right, as the one that we're going to use. Pick which version of the impulse that we're going to work with, all right. Just kind of a side note, when you're using the calculus form, it's simple enough to just run the integral because it breaks down pretty easily. When you're going to do the F equals constant, it comes with a free body diagram, okay? You almost always have to do a free body diagram to kind of get a sense of the forces in place. So it'd be like mass times gravity, there'd be the force, there'll be maybe some friction. But the thing is, you have to multiply each of these by delta time. Because remember, force times time is what gives me the impulse. So each of these bad boys becomes an impulse, and you have to kind of figure out what the resultant impulse would be, if that makes any sense. So to be equal to some sort of resultant mass times acceleration times time. This guy is what would end up being the F delta T, okay? A lot of people don't really get to see that, so that's just a quick little aside there. It's not always just going to be, you know, the force in play. Basically, if I had to use this version, I wouldn't just use F equals. I'd have to do a free body diagram to get a sense of like if friction played a role or whatever. All right, so once we did that, it was just a matter of plugging and chugging our integral and the data inside of our integral, and life is good. Okay, so that's that. Thank you for your time. If you like these videos, please actually go like them and subscribe to the channel. Got a goal. I'm trying to put up as many mechanical and electrical engineering videos as possible because these classes just shouldn't be that hard. So with all that being said, thanks for your time. I hope this helped.